Hello everyone and welcome back. So in this video, let's find the time complexity of insertion sort. So in insertion sort again, we were given an array and the approach was something like we are going to pick an element and make sure. So we are assuming that this particular half is already sorted. For the next element, we are going to pick it and then make sure that we are able to put it in the right position in our sorted array. So that was the major idea, I would say, behind your insertion sort. Now, if we actually think about it and let us see the code as well. In this particular code, if you all see, this is the code of insertion sort. Here we have insertion sort for step in range. So I'm picking up the element one by one. The first element, we always assume that it's sorted. Everyone, please make sure that you also find out these complexities by yourself after watching these videos for the same algorithm as well, so that you are able to actually revise all the steps, right? This will also help you to understand in better, I would say, overall remembering your algorithm, because to find out the complexity, you should have an idea that what exactly this does, right? So please make sure that you practice that. Now coming back, merge sort, we assume that first one is already sorted. For the second one, we now go back and see exactly what we have to do, right? Now again, because we are considering the worst case possible, worst case scenario, always we will have to make all the switches, right? So we will have to take this case, like this is, let's say, some k work which we are doing, k operations. We will have to do it every time. Okay, so this key less than array of j, okay, and while j greater than equal to 0, all of these will get executed. So let's say when I'm on the fifth element, all four elements are basically greater than my fifth element. Okay, so that is what the worst case is. So it would be something array like this, 5, 4, 3, 2, 1. Okay, and maybe you can just extend it for a large n size. If that is clear, then let us try to understand the same using the way we have understood other complexities. So for first element, I think we don't have to do that. So for first element, we are not doing any work, right? For second element, we are doing some k work, right? Because we will be comparing with one single element. For third element, similarly, we will be doing some 2k work because we will be comparing it with the two elements on the left. Similarly, if I just continue for nth element, I will be doing n minus 1 of k work, right? So again, the understanding of an algorithm is very, very important if you want to find out its complexity. I am showing you the code, but you will actually see that code is not required. If you want to find out the complexity, code is actually not required, and that's the beauty of asymptotic analysis. We don't have to write the code. Even if the implementation changes tomorrow, the problem which we faced in the very first experimental analysis, we are still good to actually find out our answer, right? Now if I add all of them, we have done this already. This is something known as 1 plus 2 dot 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 all the way till n minus 1. Okay, so in the bubble sort we saw how it is evaluated. This is coming out to be n into n minus 1 by 2 into k, right? If this is the case, let me write it a little bit on the left side, 1 second. Yeah. So n minus 1 into n k by 2. This is your final complexity, right? If I just expand it, that's going to be kn square by 2 minus kn by 2. This of course we can assume to be 0. And now this is our final complexity, which of course is lesser than c dot g of n, where I can take g of n as n square and c as, say, k by 2 plus 1. So I have bounded my particular relation. If that's the case, then of course I think we are smart, so we can write complexity is O of n square, right? That is quadratic, right? We have seen that it is also bad in the bubble sort example, how it was taking so much time. Now one more thing which I would like you to actually teach or discuss is the best case complexity, let's say, in terms of your insertion sort, right? So let me write best case complexity for insertion sort. Now in the best case, your whole array or list will be sorted. If it will be sorted, then for each and every element, once we move forward, for each and every element, of course, we will not have to do a lot of work, right? Just by doing the single comparison, we can tell if the subpart is sorted or not, right? So with that in mind, what we have to now do is, we have to make sure that we are able to understand and imagine how exactly that will work. So let me draw an array, an example. Let's say this is our array and we know that it is actually sorted in the increasing order. So let me take some values, let's say 1, 2, 3, 4. Okay. So pay attention everyone how best case complexity is going to get fine. So for 1, we will first assume that okay, this part is sorted already, that's fine. For 2, we will compare it with 1 and we will see that okay, it is smaller. So for sure we can say if anything is in back is there, that will also be smaller. Similarly for 3, just a single comparison, no more work. For 4, just a single comparison, no more work, right? If you go in the implementation as well, this particular will never get work, right? This particular thing will never be executed because this particular condition will always be true. So on that note, what we have to do or what we see is that we will just be doing some k operations, right? We will be just doing these k operations. And these k operations we will be doing for n-1 elements. Okay, so I will just write it here as well. Let me just write it a little bit nicely. Best case, and it is also known as omega, right? Omega time complexity of insertion sort. Great. So we have already seen how for the first element no work will be there, right? For the second element this time we will be just doing some k operations. For the third element as well we will be doing some k operations. No swaps will be there. Okay, so we don't have to worry, no swapping, nothing will be there. For the fourth element again we will be doing some k operations, and all the way till nth element we will be doing some k operations, right? So I hope the approach is actually clear. Again, I don't want you to remember this thing, right? I want you to explain by using the intuition and the approach. If the approach is clear, and if let's say now I add all of them, then it is going to be k plus k plus k. How many times? I think it will be n-1 times, right? If that's the case, then the complexity will be written as k into n-1, which is equals to kn minus k. Now this of course is a constant, I can take it as 0. It should be less than, now I can directly write it k plus 1 of n. Okay, so this is my g of n everyone. If that's the case, then I think we can also write that O of n is the best case complexity, time complexity of course, for insertion sort, right? So if you give it an already sorted array, it's going to take O of n time. Again, not the exact time, just the order of, as the input will increase, the time taken on all the constant and everything is going to increase by a linear relation. Okay everyone, so I hope this is clear as well. Now again, this is very important to understand how we can find out these best case complexities as well for some algorithm. Though majorly, I would say even 95% of the time, you will always be dealing with the worst case time complexities only. Okay, cool then everyone, thanks a lot. Let's meet in the next video. Thank you.